Picture this. You've got a vast open ocean. A chemical gets released into the water, right? It's so diluted it's barely even detectable. Literally just a microscopic drop in an impossibly large bucket. But somehow, months later, that exact same chemical mysteriously reaches a lethal, life-threatening dose inside the egg of a bald eagle miles and miles away. How is that mathematically possible? Well, welcome to this explainer. Today we're unraveling one of the absolute most fascinating and kind of terrifying mysteries in modern toxicology, the invisible biological multiplier. Here's our roadmap for today. We're going to start with bioaccumulation and biomagnification, move on to persistent organic pollutants, look at some historical case studies with Rachel Carson and DDT, and the tragedy of Minamata, before tackling modern endocrine disruptors, and finally, a transgenerational legacy. Let's dive right in. Section 1. Bioaccumulation and biomagnification. To solve our bald eagle mystery, we really need to understand how bodies process different types of substances over time. And that brings us to our first core concept, which is bioaccumulation. Basically, this is the net accumulation of a substance in an organism's tissues over its entire lifetime. The really crucial point here is that the rate of intake, whether that's through food, water, or just direct absorption, actually exceeds the rate of elimination. It's all about lifetime tissue loading. The chemical comes in, but it just doesn't leave. But, why do some chemicals stick around while others are just naturally flushed out? Well, the chemistry of this retention really comes down to something called lipophilicity. Think of it kind of like a bank account. A water-soluble compound, like table salt for instance, is rapidly excreted in urine. It's like cash you spend immediately. It doesn't accumulate. But a fat-soluble or lipophilic compound dissolves right into the lipid membranes and fat deposits of cells. It's stored there. It's basically a toxic savings account. And unlike a real bank account, the deposits here are guaranteed to stay. Every single meal containing that compound is a deposit, and the withdrawals, or excretions, are virtually minimal. Now, while bioaccumulation happens within one single organism over its lifetime, our next concept, biomagnification, scales this whole thing up to the entire ecosystem. This is the process where the concentration of a bioaccumulating substance increases with each successive step, or trophic level, of a food chain. Because a predator eats so many prey items over its life, it ingests and retains almost the entire pollutant load of everything it ever ate. Typically, this multiplies the concentration by roughly an order of magnitude, so about 10 times, at every single step. Tracing this classic historical example from Long Island Sound in the 1960s, we can see exactly how this builds up. We start with water containing DDT at just 3 parts per trillion. I mean, that is almost nothing. But then, plankton absorb it, increasing the concentration to 0.04 parts per million. Small fish eat lots of plankton, bumping it up to 0.5. Then large fish eat the small fish, hitting 2 parts per million. And finally, the osprey, the top predator, eats the large fish, ending up with a whopping 25 parts per million in its tissue. And this just brilliantly illustrates the terrifying mathematics of biomagnification. That osprey, at the very top of the food chain, is carrying a tissue concentration roughly 8 million times higher than the surrounding water. 8 million. No way, right? But that is the invisible multiplier at work. And it is absolutely enough to completely shut down the bird's ability to successfully reproduce. Section 2. Persistent organic pollutants. So what exactly are these chemicals that exploit this biological multiplier so effectively? Let's introduce the specific family of culprits. They're called persistent organic pollutants, or POPs for short. For a chemical to be classified as a POP, it actually has to hit 4 specific marks. Number 1, it must be resistant to environmental breakdown. Number 2, it has to bioaccumulate in living tissue. 3, it must biomagnify up the food chain. And 4, it's got to be able to travel long distances via air, water, or migratory animals. These are basically carbon-based chemicals that simply refuse to go away, which is exactly why they're heavily regulated globally today by the 2001 Stockholm Convention. Section 3, Rachel Carson and DDT. To really grasp how destructive these POPs can be, we need to look at a historical case study and the pioneering scientist who exposed it to the world. Rachel Carson was a brilliant zoologist and science writer. Back in 1962, while she was actually undergoing treatment for breast cancer, she published the landmark book, Silent Spring. The quote we're looking at here perfectly captures her radical systems-level thinking. She argued that, look,
You can't just test a chemical on a single species at the point of application and simply call it safe. You have to trace it through the entire food web, across trophic levels, and across time. This concept literally became the absolute intellectual foundation of modern ecotoxicology. Carson was specifically targeting the pesticide DDT, which at the time was being sprayed across millions of acres. And initially, it seemed perfectly safe for vertebrates. It really wasn't acutely toxic to mammals or birds. But Carson revealed the hidden biological mechanism. DDT's breakdown product, DDE, biomagnified in fish-eating birds. Once inside, it inhibited an enzyme called carbonic anhydrase in bird ovaries. And the result? Eggshells were 25 to 40% thinner. The absolute tragedy here was that incubating parent birds, like bald eagles and pelicans, were unknowingly crushing their own eggs just by sitting on them, trying to keep them warm.
Tracing this timeline reveals a pretty dynamic story. By 1963, mostly because of these crushed eggs, the bald eagle population in the contiguous U.S. crashed to a terrifying 487 nesting pairs. I mean, they were right on the brink of extinction, but catalyzed by Carson's work, the newly formed EPA outright banned DDT in 1972. And just look at the result. The eagles bounced back. By 2024, estimates show over 70,000 breeding pairs. It just proves that when we understand the causal mechanism and remove the stressor, we can absolutely reverse human-caused ecological collapse.
Section 4. The Tragedy of Minamata. While the eagle's recovery is an incredible triumph, another historical tragedy unfolding around the exact same time in Japan revealed a deeply human and, frankly, far darker consequence of bioaccumulation. From the 1930s all the way to the 60s, the Chiso Corporation discharged wastewater containing inorganic mercury straight into Minamata Bay. Now, inorganic mercury on its own behaves one way, but nature has a funny, or in this case, tragic way of altering our mistakes. Anaerobic bacteria living down in the bay's sediments biologically converted that inorganic mercury into a highly toxic organic form, methylmercury. And unlike other POPs that tend to hide in fat, methylmercury actually binds to muscle tissue. This meant it heavily contaminated the very protein source the local fishing villages relied upon every single day. The human cost here was just unimaginable. Thousands of people developed severe neurological symptoms. But the most somber realization of all was the transplacental transfer. Infants of mothers who had little to absolutely no symptoms were born with profound, severe brain damage. It turns out methylmercury crosses the placenta much, much more efficiently than it affects adult tissue. The Minamata tragedy forced the world to realize a horrifying truth. A developing fetus can be irreparably harmed by chemicals that produce absolutely no visible effect in the mother.
Section 5. Modern Endocrine Disruptors. So, we ban DDT, we have a global treaty for mercury. The problem is solved, right? Well, unfortunately, no. The principles of the invisible multiplier apply directly to the chemicals surrounding us right now.
Let's take a look at a category called endocrine disruptors. These are chemicals that interfere with the body's hormonal signaling system, basically mimicking, blocking, or altering natural hormones. But here is the critical thing you really need to take away from this. Unlike the classic POPs that need to build up massively over a lifetime, endocrine disruptors can trigger devastating effects at almost unimaginably small scales. We are talking parts per trillion. Why? Because that is the exact microscopic scale at which our body's own hormones operate. Let's run through a few of the modern chemicals currently under intense scientific study. First up, we have atrazine, a widely used U.S. agricultural herbicide, which laboratory studies show can actually demasculinize male frogs at extremely low concentrations. Then there's BPA, found in plastics and can linings, which acts as an estrogen mimic and has been linked to cancer in animal studies. Next, we have PFAS, the notorious forever chemicals from nonstick pans and firefighting foam, which are linked to immune issues and kidney cancer. And we even have pharmaceutical synthetic estrogens from things like oral contraceptives, which literally pass right through wastewater plants and cause estrogenic disruption in wild fish populations. To give you a real idea of the sheer potency of these substances, let's look closer at those PFS forever chemicals. The carbon-fluorine bonds in PFS are among the absolute strongest in all of organic chemistry. Because they're so persistent and so active at such incredibly low levels, the EPA in 2024 established a maximum contaminant level for two types of PFS in drinking water at just 4 parts per trillion. That is among the strictest standards ever set in regulatory history. Just to put that into perspective, that's roughly 4 drops in 1,000 Olympic swimming pools. That's how little it takes to cause serious concern. Section 6. a transgenerational legacy. Let's tie all of these threads together and look at the overarching theme of these really insidious ecological threats.
Let's quickly review the 4 terrifying traits we've uncovered today. These substances accumulate silently over a lifetime. They biomagnify and multiply across our food chains. They persist in the environment for decades, long after the source is actually shut off. And, perhaps most chillingly of all, they can damage the next generation far more severely than the current one. The true cost of releasing these chemicals is almost entirely hidden from us at the time of release.
And this harsh reality is the scientific bedrock for what we call the precautionary principle. Because the effects are irreversible and intergenerational, this principle basically states that the burden of proving a chemical is safe should fall squarely on the manufacturer before it hits the market, not on society after the damage is already done. We're finally seeing policy try to catch up to this biology, kind of like the 2016 reform of the U.S. Toxic Substances Control Act, which actively attempts to require safety evaluations before widespread market entry.
Which leaves us with this final vital thought. As Rachel Carson taught us over 60 years ago, nature is an interconnected web of systems, and time is a multiplier. So I want to leave you with this question to help reconsider how we look at our modern world. If a chemical company proves their shiny new compound isn't acutely toxic to a mammal today, knowing everything we now know about bioaccumulation, food chains, and endocrine disruption, is it truly safe for tomorrow? Really think about that the next time you hear about a new wonder chemical. Thanks for joining me on this explainer, and as always, keep asking the big questions.